This video is an introduction to the IPFS Service Provider software project that is maintained by the Permissionless Software Foundation. The scope of this video is to explain what it is, why it's important, and how to use it. So the purpose of this video is to provide a foundational education for PSF members. This IPFS Service Provider software is a boilerplate. It's used to create several other PSF projects, which I'll cover later in the video. It's also intended to inspire people to hack on this project and contribute to the code base. It's 100% open source. It's got 100% unit test coverage. It's MIT licensed, so people are welcome to take this, do whatever they want with it, and hopefully contribute back to the project. Also, the purpose of this video is to explain what it is and why it's important. So what is it and why is it important? It's the PSF, or the Permissionless Software Foundation. It's their way of interacting with the IPFS network. We've gone through several evolutions trying to integrate with the IPFS network in our software. This is the latest iteration. It's got a lot of improvements. This new iteration is based on Helia, which is the new JavaScript IPFS node implementation. It's much lighter weight. It's relatively new. As I'm recording this, it's October 2023, and it was released in February, so it's still very new. It's a massive improvement over previous IPFS nodes that we've tried to use. The other reason why this is important is the IPFS service provider is a boilerplate for other PSF projects like I've mentioned. So the demo I'm going to give today, interacting with the REST API, that feature is baked into these other projects. So if you can interact with this, you can interact with those in the same way and with extra features. So the main big benefit that Helia has given this project is it significantly reduces bandwidth. This has been an issue that we've always dealt with trying to use the Go IPFS implementation, and prior to that the JS IPFS implementation. So it's much more than a 10x reduction in bandwidth. It lets people run these IPFS nodes on very small CPUs and small internet connections, or low bandwidth internet connections. And another big feature is that we currently have achieved 100% unit test coverage. So that is really advantageous for an open source project because it gives you the confidence of adding features without adding bugs to old features. It makes it easier for open source developers to contribute to a project because all they have to do is maintain that 100% unit test coverage moving forward. So it makes it much easier to collaborate. Okay, how to use it. Let me just jump into the demo and then I'll give a little more background on what's going on. So down here I have a little virtual private server running Ubuntu version 20, I believe. It's either 18 or 20. And I'm tunneled into it, and I've got node 16 and npm 819. So the only dependencies that you need to run this demo is Node and MongoDB. And if you don't have MongoDB installed, there's a simple script for that. So where's the software? It's here in GitHub under the Permissionless Software Foundation GitHub group, and the repository is called IPFS Service Provider. So I'm going to clone this repository. And at the same time, I'm going to tunnel into the virtual server, and I'm also going to clone psf-bch-wallet, which is the command line app that we're going to use to interact with our IPFS node. So once I've cloned them, I can go in there and install npm dependencies. Okay, and so I'll give that a minute to install. With the npm dependencies installed, we can now activate the software. So I'm in psf-bch-wallet, and in fact I'll make this a little bigger. The first thing to do if you're brand new to the command line wallet is to run this help. Now all commands are prefixed with this bin run, and then you give it a command. And if you run this help command, it'll show all the other commands that you have access to. So these are all the commands. It's kind of dizzying right now. What we're going to focus on in this version, one second. What we're going to focus on are some IPFS prefix commands, which are not shown by default because it's kind of an advanced setting. So what you're going to want to do is go bin run conf-k. We're going to set a key value. So k for key, and the key is command IPFS, and the value is true. And now when we run help, these IPFS commands appear. So these are the commands we're going to run. They're also available in the GitHub README. They're not hidden there. Right here, so you can get the help for these commands here. That might be an easier way for some people. So there's 3 commands right now to check the status of the IPFS node, to check the peers that the IPFS node is connected to, and to check the information about relays, circuit relays that we're connected to. Circuit relays help nodes connect to one another that otherwise wouldn't be able to connect to one another. So it adds, as it's like a middleman, and it shuffles messages between 2 nodes that can't directly connect to one another. And these messages are encrypted, so the circuit relay doesn't have any access to the message itself. It's just helping messages get across. So back over here in the IPFS service provider directory, we're going to start it with npm start. And this starts with a default debug level of 2. There's it can be 0, 1, 2, or 3, and it controls the level of verbosity, or how much information gets displayed on the command line. Yeah, okay, so it's a level of 2. And anyway, so our node is up, and we can now begin to query it with these commands. Although first, we have to set another config setting. And actually, if you just run pretty much any command, well, let's try the wallet list command. You'll want to set the this REST URL setting to point to your local instance of IPFS service provider. So when it starts up, by default, it starts on port 5020. So we're going to say localhost 5020. So connect. This is the. Oh, I need to prefix that with conf. Just like that. So now if we run the conf command, we'll see that there's another field here, and we can check its value with just the K flag. So now we're in business. So now if we run status, IPFS status, this is telling us the status of our node, the node that is running inside of IPFS service provider. So this is our IPFS ID. These are the multi-adders, connections, ways to connect to it that the node is aware of. The node gets assigned a Bitcoin Cash address and a simple ledger address. These are used for end-to-end encrypted messaging, but they can also be used to send money and tokens. And so the other command, IPFS peers, will display a list of all the other IPFS nodes that it's connected to. So it's currently connected to 3 other peers, and if we want to get more information on each peer, we can do a -a flag, and that'll give us all the information it has. It doesn't currently have any other information. It's because it's behind this firewall, it's having a hard time getting data. The last command is relays. This tells us all the circuit relays that we're connected to. So we're currently connected to looks like 6. 1, 2, 3, 4, 5, 6. So we're connected to 6 different circuit relays. And again, it's having kind of a hard time getting the announcement information from them right here in this demo. But once it gets some announcements information, it'll populate that data here. So this is, okay, so there, it looks like it's getting more information now. It's had more time to connect. Here we go. So I ran IPFS peers with that A flag. So this is all the information about all the peers that it knows. So these peers are periodically broadcasting these messages every 2 minutes, just to say, this is the API I'm running, this is the version I'm running, here's a little more information, here's all the multi-adders on how you can connect to me, and here's my Bitcoin Cash address, here's my simple ledger address, here's my encryption key for sending me encrypted messages. And so basically I've demoed the software. If you want to just dive in and get started and start playing with it, this is how you can do it. Let me go back to the slides and explain a little bit about what happened. Oh, and I should mention MongoDB. If you don't have MongoDB installed on your system, there is this install MongoDB script in the ipfs-service-provider repo. So you can just run it like that, and it will install MongoDB on your system. And again, I'm using Ubuntu 18 or 20. This will work. And if it's 22, you might have an issue installing Mongo. There's still some issues with installing MongoDB on Ubuntu 22. Okay, so that's how to use it. So let's talk about dependencies. So what I just showed in this demo is we used psf-bch-wallet to interact with ipfs-service-provider over its REST API. So that's what I just demoed. ipfs-service-provider depends on another library called helia-coord, which I'm also going to cover, and then ultimately helia-coord sits on top of Helia. So coord stands for coordination, but it's also kind of a double entendre. It's like a tie that binds. So what helia-coord is it's a small, lightweight library, and it controls the IPFS node, which is Helia, and sets up this on-the-fly mesh network. That's what we were seeing here with all this peer data. These are other peers in our mesh network, and mostly all it does is it just sets up a series of pub sub channels, and that's what lets all the nodes in our mesh network communicate with one another. So I actually want to jump over here to helia-coord is also in the GitHub repository. This is an NPM library, and if you go into the dev docs folder, there is this theory of operation. And so if you're interested in Helia and you want to understand, or helia-coord, and want to understand more of what's going on, this is a great document to start. It's very high level, but essentially what it's doing is it spins up the Helia node, connects to a series of bootstrap nodes that the PSF maintains, and then it starts setting up pub sub channels. So the main channel is the coordination channel, and this is where that announcement information comes through that I was showing on the command line. So every 2 minutes, every node sort of announces itself on this coordination channel. So a new node joining the network just has to listen to this channel to discover all the other peers in this mesh network. And in those announcement messages, we'll have information about how to connect to it. And then once it sees a new peer, it will try to connect to that new peer. And if it can't connect directly, it'll try to connect to it through a circuit relay. There's also another public channel called the CoinJoin channel. That's not fully developed yet. I'm going to skip it, but it will be used, if you know what CoinJoin is, it'll be used for CoinJoin transactions. So those are the main public channels, and then there's these private channels. And the reason they're private, they're not really private, but what it does is each node will establish a pub sub channel for itself based on its IPFS ID. And it is only used for receiving, and it's only used for receiving encrypted messages. If it receives a message that's not encrypted, it will reject it, and it will never send anything out on this channel. It will only receive on this channel. So this is how other nodes send it information. Is it encrypts it and sends it to its receiving channel. And at the same time, the node will connect to all the other nodes it knows about on their private channels, and that's only used for sending. So if my node needs to send a piece of information to another node, it will encrypt the data using that node's encryption key, public key, and then send it on its receiving channel. And so that's basically all that helia-coord does. Is it just sets up these pub sub channels, and then there's a series of interval timers that just basically maintain the mesh network. So if a connection it gets lost between two peers, it'll automatically try to reconnect. If a new circuit relay appears on the network that it hasn't seen before, it'll connect to that. It measures the latency between itself and the other nodes, especially the circuit relays. And so it'll optimize its connections to achieve the lowest latency connection. So this is all happening behind the scenes. And that's what helia-coord does. That's why it exists. So that's why it's important. And so IPFS service provider is really just a REST API that sits on top of helia-coord. And it provides this REST API, and it also provides a JSON RPC over IPFS. So anything you can do with a REST API, which is the standard for computers to talk to one another over the internet today, that protocol is great, but it's also not very difficult to censor it. And anything you can do with a REST API, you can do with this new JSON RPC that IPFS service provider provides, and that makes it highly censorship resistant in the fact that the message can go through any node in the mesh network, or any node on the IPFS network actually, in order to reach its goal. And so it's much more difficult to censor than a REST API, and you can achieve all the same things that a REST API can do. So that's why that's important. And that's the main value that IPFS service provider provides, and that's why it's a boilerplate for other projects. So some documentation I just want to bring to your attention if you want to dig into this a little deeper. I talked about the theory of operation. That's worth a read. I also pointed out the README and the help file command for psf-bch-wallet. That's also worth checking out. The file layout in both, if you're a developer and you really want to look at the code, both for helia-coord and for IPFS service provider and for most PSF projects, follow this clean architecture paradigm. And there is a link to that here in the IPFS service provider README under a section called file structure. You can click this link and it'll take you here to this article and videos on clean architecture. This is there's a lot of thought here behind this idea, but basically the files are laid out in this structure where there's entities, use cases, adapters, and controllers. I won't go into this very much, but if you are a software developer who cares about building apps that can manage complexity, reduce bugs, and become increasingly complex over time, this way of laying out your files and structuring them is very key. Nest.js is a framework that uses these concepts. They lay them out a little differently, but they use the same basic ideas here. And so that's some documentation I wanted to point you at. So the other big reason why this is important is that this is used as a boilerplate for a lot of other PSF projects. So I want to talk about that for a minute. The pay-to-write database, you can access that documentation at p2wdb.com. This is a great introduction if you want to read more about the pay-to-write database. What it provides is a censorship-resistant peer-to-peer database and file pinning service. So this is a huge, major focal project for the Permissionless Software Foundation, is this ability to do for data what Bitcoin did for money, is to make it permissionless and censorship resistant for putting data out into the public, like a database, but then also distributing large files, which is where the file pinning service comes in. And that's why we need, this software is critical for bridging this gap between the IPFS network and a blockchain network like Bitcoin Cash. There's also the cache stack, which is very important project for the PSF as well, and you can access that documentation at cachestack.info. And this goes into detail on the JSON RPC that I just mentioned. We have a Web 2 cache stack and a Web 3 cache stack. So Web 2 uses REST APIs and all that Web 2 technology. The Web 3 cache stack uses this JSON RPC. It functions exactly the same, but what it does is it lets you run your infrastructure at home on a normal desktop much cheaper, and then securely give access to that to other members in your network. And it significantly reduces cost and significantly increases the censorship resistance. And it's for building mobile apps that have a Web 2 experience but can tap into this censorship resistant component of blockchain and IPFS. And then finally, this is a project that's kind of on hold for now, but will hopefully grow in the future, is collaborative CoinJoin. And that project is at ccoinjoin.com, so two C's at the beginning, for collaborative CoinJoin. And you can read about that documentation. And this is a JavaScript framework for wallet developers who develop apps on your phone for working with Bitcoin Cash and tokens and other blockchains, to easily incorporate CoinJoin into their wallet app so that more people can have financial privacy. And again, its censorship resistance is a focus there, because what good is it to have financial privacy if you get censored from using it? So that's another big focus. So hopefully what I'm imparting on you is that this IPFS service provider is important because it's a fundamental building block for more advanced applications like what I have listed here. And this is what I'm hoping that more people will join in, hack on it, contribute code, and use this as a boilerplate for their own projects moving forward. And then you can tap into the IPFS network as well as the Bitcoin Cash blockchain. It also is very easy to fork for the eCash blockchain and other Bitcoin-based forked blockchains.